Okay. Now, if you take the closure, so this is nothing but the closure of, so which we didn't bother on the top here. It's a closed set. Okay. Now, the third thing that we get into this structure of these spaces I'm talking of. Okay. So the structure that we have here, so structure. You have Y to be a subset of X is called a subspace. If Y with this norm, okay, this is with the norm, okay, is a norm linear space in itself. It's a norm linear space. Okay. This is called a subspace. Please note, if you say subspace, the norm is inherited from X. This is called parent. Okay? Is this clear or not?
Yes, sir.
Can you give an example of a set which is not a subspace? So let me give you, so you have LPR. This is nothing but the set of all sequences, real sequences, such that summation mod xi raised to p I equal to 1 to infinity is told me. Go ahead.
I think set of is rational numbers.
Hmm?
Is rational numbers.
Hmm.
Is also not a subspace, sir.
Subspace of what?
Subspace of R.
This is linear algebra, no? You are talking Q is a subset of R, right?
Yes, sir.
Suppose you take 1 multiplied by root 2. It is not in Q. So it is not a subspace.
Yes, sir. And same way is rational numbers also, sir.
Huh?
Is rational number.
I'm talking of rational, no? Q is rational.
Yes, sir. Yes, sir. Yes, sir.
So Q is not a subspace,
Yes, sir.
right? If it
Yes,
is a
sir.
subspace, if you take any so you see if X is in X, then alpha X has to be in X. This is essential. Clear?
Yes, sir.
Is it clear or not?
Yes, sir.
Not. I'm not very happy the way you are taking. See, what is a non-linear space? X is a set, K is a scalar, then you have two maps, plus from cross X to X. And scalar multiplication from K cross X to X, such that, right? All that properties. Huh? Is it clear? So when you take Q as R, root 2 is in R. Therefore, if you look into 1 into root 2, then it is not in, because it's irrational. Okay? This is rational. Is it clear?
Yes, sir.
I want to give a non-trivial subspace. Okay? So what I'm saying is you look at L1, L1R. Okay? That is summation sequences. This is finite. I equal to 1 to infinity. Okay. Now look at C01. This is a subset of L1 R, right? Let me take capital L1. Okay. So this is not that. This is summation mod of fx dx between 0 and 1 is finite. So instead of L1 R, let me take L1 0 1. Okay. This is the condition that you have for the. Let C01 is contained in this, not this L1. L1. Norm of f infinity is maximum of mod fx 0 less than or equal to x less than or equal to 1. There is another norm on this. That is L1 norm. What is that? F of L1 norm, which we write it as 1, is integral 0 to 1 mod fx dx. Okay? These two both are norm on that. So when you look at C01 with sup norm, okay, with this norm, is not a subspace of L1. Is it clear? Here the norm is sup norm. Therefore, this C01 is not inheriting the parent's norm. Therefore, this is not a subspace. Clear?
Yes, sir.
जोर से बोलो.
Yes, sir.
You understand, no? What's the subspace? The subspace means it has to inherit the norm from the parent space. Otherwise, it's not a subspace. It may be a non-linear space by itself, but it may not be a subspace. Okay? Now tell me one thing. Your revision, you want it this way or you want me to read the book? Hmm?
Sir, this way.
Hmm?
Sir,
This way is good?
yes, sir. Yes, sir.
So after defining the non-linear spaces and the subspace, now we get into examples. Okay? ये क्या हो गया यार? हमने जो लिखा था वो कुछ भी नहीं आ रहा. अभी तक लिखा कहाँ चला गया? सब गायब हो गया. One minute. Huh? Okay, now it has come. So we come to examples. This computer is creating problem. 1 minute, huh? Okay. So now we come to the examples. What are the space? What is a natural norm? What we think that you raise this to infinity mod xi raised to p raised to 1 by p. Sir, from where do you get this? So you go back to geometry, look at small L2, okay, R. This is nothing but, so you can take L2 too, okay. This is nothing but R squared, right? What is the norm here? When you take x1, x2, okay, the norm of this, what we call this a length in R2, it is summation xi square I equal to 1 to 2 raised to half. So this power 2, you get a raised to half. This is the motivation. And therefore, this motivation, instead of p equal to 2, you take any p greater than or equal to 1 there. So this you expect it to be an arrow. Expect it to be an arrow. So what is that we have to show here? Norm of x is 0 if and only if x is 0. This is simple. Norm of alpha x is equal to mod alpha into norm. This is also simple. By the definition, it follows. Problem is with respect to this part, triangular inequality. Okay, that is what I was telling you. So you need to prove the triangular inequality here. For this, you need Holder's inequality and Minkowski's inequality. This is actually this one. So Holder gives you Minkowski's inequality. Okay, so we have to prove this first. So whenever you talk of a lecture here, you first prove Holder inequality, and then you use it to prove Minkowski's. Inequality. Then these two will imply this norm is a norm on LP. Clear? In order to prove this Holder, we prove Young's inequality. What is Young's inequality? AB less than or equal to 1 over P A raised to P plus 1 over Q B raised to Q, 1 by P plus 1 by Q equal to 1, P greater than or equal to 1. Okay? Is this clear? So what we did in the class, we first proved Young's inequality, then proved Holder, then proved Minkowski, then we said it's a norm. Okay? As a consequence, what we said is the ball of radius r is convex. We proved it. This is true in any non-linear space. But when you take 0 less than p less than half, sorry, less than 1, this LP with this norm, okay, whatever the norm that we have, is not a norm. This LP norm is not a norm. What is the norm here? Summation mod xi raised to p raised to 1 by p. 0 less than p less than 1. This, if you define it as norm p, norm x, sorry, then this is not a norm. How do we show it? We don't show through Minkowski's or Holder's inequality. We show that the ball of radius 1 is not convex. This I did it in the class. So if the ball of radius 1 is not convex, then this cannot induce a norm. Why? Any norm will induce a convex set. B0R is a convex set. Is it clear?
Yes, sir.
Okay? It's an indirect proof that you don't go through Holder and whatnot. You go through the fact that the unit ball is not convex, you show it. Okay? So that's the point which you should understand. So this is about the structure of the space. And now we look at parts of subspaces, etc. Then you have Jensen's inequality, etc. Okay. So you have things like Jensen's inequality. That you have 1 less than or equal to p less than r. Then if you take an element x in LP, okay, then norm of xr is less than or equal to norm of x in LP, right? We proved it, if you remember.
Yes, sir.
What does this mean? Huh? You see, the inequality is one thing. What does this mean? This means that if the sequence xn converges to x in LP, this will give you the fact that xn will converge to x in LR. Why? Because when you look at xn minus x in LR, this is smaller than or equal to xn minus x in P. This goes to 0 because of this, and therefore this will go to 0. So this LP norm, this P norm is called stronger than LR norm. LP norm is stronger than LR. Okay? So this is one consequence. You see, one thing is that you understand what it is. The second thing is what it implies, what it means to you. Right? See, it is something like this. Suppose you have money. What does that imply? It implies that you can go to a shop and buy something if you have enough money. Right? Now I ask you, you go to a shop and buy something and I don't give you money, then you can't buy. That is what I'm saying. So if it is a norm, then the unit ball has to be convex. If the unit ball is not convex, then it cannot be a norm. It's something like not having money, you can't buy it. Analogy is not that good, but chalega. But it gives you the impression. Okay? And then you have several spaces, So you have all sorts of subspaces. C0, which is something, C1 is something, etc., etc., etc. So this is about the structure of the spaces. Then we come to linear operators. So we come to linear operators. So you have two vector spaces, M and N. You can take even non-linear space, okay? Or the same scalars. This is important. So T is a map from M to N. If T of x plus y is Tx plus Ty, and then T of alpha xy is alpha times Tx. These are the conditions of a linear operator. Okay. This is algebraic. This is vector space linear algebra definition. What is in function analysis? T is continuous if xn going to x in M implies Txn goes to Tx in N. This definition is difficult to do it. So what we do is we show the following are equivalent. 1. T is continuous at 0. 2. T continuous everywhere. 3. T norm of Tx. Okay. Is bounded by some constant times norm x for all x in x. 4. You show that norm of Tx is bounded by k times norm x if norm of x is less than or equal to 1, etc., etc., etc. Okay. These are 5, 6 conditions we show. And what we now say is that T is continuous if any one of the condition is satisfied. T is uniformly continuous. I have given you 5, 6 definition in the notes, and you can also have a look into the book of the dancer's notes that I have given. Right? Do you have any doubts on this?
No, sir.
Okay. Then Rishabh, tell me how long you would like to sit in the class? 1 hour?
Yes, sir.
Because you tell me the time, so that I'll stop after that. Okay?
Till 5, sir. Okay.
That's 1 hour, no?
Yes, sir.
Let me stop for a while. Okay? Let us take. Do you think you are getting what you wanted?
Yes, sir. Yes,
Hmm?
sir. Yes, sir.
Srilaka, are you getting what you want? Pragya, is this what you wanted as a revision? Pragya, Srilaka, not even talking, huh? अनम्यूट तो करो, बात करो अनम्यूट करके.
Yes, sir.
M005. I don't know what your name is. Are you getting what you want? Tanush Reddy, are you getting what you want?
Yes, sir.
Shall I continue this way? Or should I
Yes, sir.
or should I take the notes and read it? Which one you want?
Sir, take the notes. It will be little bit faster. Then you cover all the topics, sir. Okay.
I'll open the notes, huh?
Okay, sir.
But there are something which you may miss it. That's why I'm worried about. That is why I'm little bit hesitant in opening the notes. Anyway, I'll open it. Just 1 minute. I'll open that answer. It's opening. Just wait, huh? Are you able to see the notes?
Yes, sir.
Okay, so I am not going to do the quotient space, so I will not ask you any question on quotient space. Okay, that can take our life simple. Suppose so this quotient space I will leave it now. I will come and teach it to you in person. It's slightly involved. Okay, not it is difficult, but it's a headache to do it. Okay. So we are talking about the Banach space, etc., etc. Stone-Weierstrass theorem has been done in the Raj. Okay, so I will not get into that. Essentially, I have to go to linear operators. Okay, this is what I was saying. Base theorem I have not done. I will do it when I need it. Okay. Open mapping theorem also I will do it when it is needed. All right. Where is the preliminary things? Huh? And linear operators, I don't see it anywhere. Just 1 minute. Huh? This is the what I was talking to you a minute back. Using Young's inequality, I mean, you prove it for p prime equal to infinity also. We prove what is called the Holder's inequality. Okay, 1 less than or equal to p less than infinity. P prime is the conjugate exponent of p. Then summation mod xi yi is less than or equal to norm xp into norm yp prime. So how we do it? We do it through the Holder's inequality here, Young's inequality. Then we show that for 1 less than or equal to p, this is a norm. And we also show so this is the what is called the Jensen's inequality. Instead of R, he is using Q. Chalega. Okay. So here you show this proposition 2, it says norm of xy raised to p. You show that this is this part, and then you get the what is called, you use the fact that it's a conjugate prime. Then norm of xy, x plus y raised to p will be less than or equal to norm of xp plus norm of yp into norm of x plus y raised to p. Now you divide by this norm of x plus y onto the other side, and what you get is the norm of x plus y, p norm is bounded by norm of x plus. This is the triangular inequality. So this is the consequence of the Holder and Minkow's case. And therefore LP norm is a LP, whatever the norm we have defined, it's a norm. And then some consequences. And then you use it to sequence spaces. This is what I said. After you prove the Holder's inequality and this one, you go to the sequence spaces. Then you define the sequence spaces, etc., etc. This is what you do. Okay. And then you look at the most important theorem that this is something which you should understand here. How to construct something which is in LP, which is not in LQ. The summation 1 over I equal to infinity is something which is used heavily. So essentially, the convergence of this series is used. Okay, I'll come back to that again. Okay, now we prove what is called the all these spaces are complete nonlinear spaces. Complete nonlinear spaces means as metric spaces, they are complete. Complete means every Cauchy sequence will converge. That is the theorem 7.5. With this inclusion, this is part of the Jensen's inequality. And L1 and L infinity, you can separately prove it. Okay. Okay. How do you prove that this is a Cauchy sequence? What you understand is that in this LP norm, the mod of the xith coordinate is always bounded by the norm. Let me just explain to you. Okay. The major, see, every theorem has something called a key. Okay. So if you take if you take x in LP, this sometimes you write it this way also. Okay, don't worry. So if you take x in this LP, then this norm of x is nothing but summation mod xi raised to p raised to 1 by p. Instead of writing 1 by p, I'll put a p here. Okay. So that tells you this actually implies mod xi raised to p is less than or equal to the norm of x raised to p. So that tells you that the component, ith component or the ith term is always bounded by the norm of p. This is used frequently. Okay? How is it used? I'll show you now. Okay? So in order to show that this LP is a norm, what we do is we take a Cauchy sequence. All right. Where is the proof? So he doesn't bother about the LP, etc. He looks at only the case when you are looking at if one is less than p, less than infinity. So what he says is that this is also true. Okay. Okay. So we finally prove the completeness. This is important. You take a sequence Cauchy in LP. What is the meaning of saying Cauchy in LP? Xn minus xm norm p is less than epsilon if p nm p is large. But if you look at the ith component of xn and the ith component of xm, that is xin minus xim, that is the ith component of this difference, is always bounded by this. That's what I was telling you. Okay, if this sequence xn is Cauchy, then this sequence xin minus xim, you fix nm, then that sequence xin, this xin sequence is Cauchy in R. You are fixing n here, you are varying I. Okay, that is you are looking at as a column. Since this sequence is Cauchy because of the condition given that xn is Cauchy, you get this will converge to a limit. The next part is you do a bit of algebra. You show that this xn minus xp is also bounded. Okay? This I have done it in the class. Is it clear or not?
Yes, sir.
This is an important result. Capital LP convergence, I have not done it. It takes time. I will do it after your exam is over. So this is the Lebesgue space, and we had the Holder's inequality the same way, the Holder's inequality. Whatever you had the sum, here it will be induced by the integral, nothing more. So that is the question of. So now we come to bounded linear operator and continuous functions on the the space. So let E be a non-linear space and U be a map from X going to E, etc., etc. Supremum of E. Then we have bounded this one. So this also you can show it's a nice complete space. Okay. So this also we had done. Now we look at basic properties of the bounded linear operators. When do we say a set is bounded? A set is called bounded if it lies in a huge ball of radius m. Some people define the diameter. You say the diameter is finite. Both are the same definition. Okay. So if U is contained in a huge ball of radius m, then you say that the set is bounded. It's not going up to infinity. That's what it means. Okay. So if you have two non-linear space f and t, then we denote the homomorphism from E to F to be the set of linear operators from E to F. If you don't like homomorphism, don't do it. You simply say they are the set of linear operators between E and F. So L of EF means T is a linear operator from E to F and T is continuous. L for linear and continuity, E for the domain, F for the range of that operator. So this T is a map from E to F. It is linear and continuous. We set this notation. It's more a notation. So if E equal to F, you don't write LEE, you just write LE. Okay? Now, first thing that we do is the following. If T is a linear map from E to F, then the following are equivalent. T is uniformly continuous. T is a continuous linear operator from E to F. T is continuous at 0. T is bounded. You have to be careful what this T is bounded. T bounded means T maps bounded sets to bounded sets. So be careful with this definition. Okay. God. What I'm saying is T from E to E is bounded. It means that T maps bounded sets to bounded sets. Right? This is the definition of T is a bounded map. See, why I'm saying is you have to be careful. Right? Linear in the function analysis, T is a bounded operator means it maps bounded sets to bounded sets. Okay. Do you understand this or not? Huh?
Sir.
You see, in the real analysis, क्या हो गया यार? Okay. In real analysis, a function f is bounded if mod fx is bounded by m for all x, right? This is not the definition in function analysis. Function analysis bounded means it maps bounded sets to bounded sets. So understand this. This is not the definition. These two are not the same. So the definition in function analysis that something is bounded means the operator is bounded means it maps bounded sets to bounded sets. So these are the 5 theorems which these 5 we are equivalent. What do you mean by equivalent? Equivalent means that if one implies the other, any one of them will imply all other things. I have given this proof to you anyway. Not a difficult proof, but nobody will give the proof, something like this. So what you do is, having this one, you take T to be a linear operator from E to F. Since it maps bounded sets to bounded sets, so you have this infimum of alpha such that naram Tx is less than or equal to naram alpha x. So you can define the operator naram to be this. You define the naram, you define a function naram T equal to this. Now we call this as a naram, but we have to show it's a naram, okay? So it is shown that it's a naram in the next theorem. Suppose T, then naram of Tf is less than or equal to this, etc., for all over this. And you also have the supremum of naram Tx or naram E, x not 0. It is same thing as supremum of naram Tx, naram x equal to 1, supremum of naram Tx less than or equal to 1, etc., etc. Okay? So any one of this is bounded, will give you all other things are equal. So whenever you have a linear operator, you can always use this sort of notation. Naram Tx is bounded by naram T into naram x. That is what you have to understand from this particular inequality. Okay. So this supremum naram x less than or equal to Tf is less than or equal to norm t is also supremum of this is something which is true. These are the 5 equivalent definition. So one may not ask in the exam all the things, they may ask you to show only 2 of them. Not a big issue. So the space L of EF with this is a non-linear space. Now you show it's a non-linear space. Now you actually show it's a norm. So norm Tx equal to 0, you show it is. Norm T is positive is obvious. And then you show that it is 0 if and only if T is 0. That is also shown. And these are the 3 properties that you show. Now, what is written, what is not written in these notes, that you have to see it. Okay? What I'm saying is that if you have T bounded linear operator from X to Y, then norm Tx is less than or equal to the norm T into norm X. This is what you should take home from you, right? The question is that if T is from X to Y linear and T is 1, 1 on 2, then T inverse exists and is linear. This is algebraic definition. Okay. Now, if norm Tx is greater than or equal to alpha times norm X for all X, this implies T inverse is continuous. This is called lower bound. This is not written in your book, in your notes, but it is there in other books. How do you show that? Since T is 1, 1 on 2, okay, assume T 1, 1 on 2. So you call S equal to T inverse. Okay. Now what does this give you? Right. So this Tx, right? So if you take T of X equal to Y, since T inverse exists, Tt inverse of X will be Ty. So this will be, okay. So Tt inverse of X is actually, so what you get is Ty, sorry, Sy, T inverse of Y. Okay. This is T inverse of Y. So S of Y, norm of this will be bounded by this 1 by alpha into norm by. But that theorem what we have shown is that this implies that S is continuous. That means this condition, okay, this is not written in the book, that's why I am telling you this, okay. Just 1 minute. Huh? So if T from E to F, or even E to E, okay, is such that norm Tx is greater than or equal to alpha times norm X, alpha positive for all X, this implies T inverse is continuous. So if T is continuous, plus norm Tx is bounded below by this con, then this implies that T is a linear isomorphism. from E to E. You can take F here. Okay, you can even take F here. No problem. Okay. So for a linear isomorphism, what you need is T to be continuous, and you want the T to be lower bounded. So that gives you the isomorphism. Okay. Unfortunately, this part is not written in these notes. Almost I have revised, except that I have to show some few things about Hahn-Banach theorem, etc. Probably you can read it up yourself. If I mistake not, right? If I mistake not, Rishabh said you stop at 5. Am I right? It is 5 o'clock and 1 minute. Shall I stop? Hello? Am I audible?
Yes, sir. You are
Yes, sir.
It said stop at 5, so I am stopping. Okay?
Yes, sir.
So only thing what I have not done is the part of Hahn-Banach theorem and functionals. You read it up yourself. Okay?
Yes, sir.
Okay.
Yes, sir.
Bye.
Thank you, sir.
Yes, sir.